want to take No, I have voice, I thought. What? No, no. I don't like. I did not think that through for now. I just don't want it.
Happy Halloween. Who's gonna go trick or treating?
Too old for
Who's
that.
going to a party? Is there not a single person dressed up? What's that? I see. So you could dress up to do it. Seriously? What's that? Those are fun. All right, so let's get going. So, right, last class we introduced for the first time the idea of classification and what it meant, and how with a classification model you have a decision boundary, which is kind of analogous to a regression curve and yet still different. And so we saw some pictures about this. And we also had this idea that the further away you were from the decision boundary, the more confident the prediction, which is not something you would see in regression. And then we went through in detail how, what motivated, from one viewpoint, logistic regression, and also showed how to do parameter estimates, and then that it was convex, and also showed how you could generalize this using softmax regression with this softmax function. And then so we saw these forms like this. And then we also showed that if you want to find out how to see the form of the decision boundary, then you check where the probability of each class is equal, and then you rearrange the algebra to get a function of x. In this case, it's a line, but it's a linear function of x. And so we had a linear boundary. And so just to finish off that lecture, I'm going to make one more comment, just one because it's interesting and you should know it, and also that you hear this term all the time nowadays as a loss function, which is the cross entropy loss. And actually, when I was in grad school, no one really talked about that. We just talked about the log likelihood as a loss. And so actually, when I first started hearing people say this, I was thinking, like, why are they using this other loss? And there's a very simple reason, which is that they're actually equivalent. And so this is a good thing to know. But if you come from a more statistical, traditional background, I think, like I do, you will always think of it as maximum likelihood estimation. But it turns out that there's several things that are all related, and knowing that they're all kind of the same thing can be useful downstream. So we're going to just go through that now before we get on to the next topic, which is generative versus discriminative models. Are there any questions at all from last time? Okay. So before we get there, a key quantity is gonna be the Kullback-Leibler divergence. And so we're gonna start off with going through a derivation where we start the Kullback-Leibler divergence between two things with respect to logistic regression. And then we're gonna show from that we get an equivalence with something called the cross-entropy loss and also maximum likelihood estimation, or maximizing the log likelihood. Okay, so, but the Kullback-Leibler divergence is really just a way to think about measuring the difference between two distributions P and Q. And so sometimes when you're in various places in machine learning, you might want to have one of these be parameterized and then minimize that so the one distribution looks like the other. And this is the form it takes. So if P and Q are two different distributions, or you can think of them as random variables, then you can, if you sum over all x's in the discrete case, then this is the form that the KL divergence takes. And you'll notice that it's not actually a true distance measure because it's not symmetric, right? So if I flip P and Q around here, I don't get the same answer. This is actually in some ways problematic, but it's sort of, we won't talk about that in this class, but it's very convenient to work with, and so that's one of the reasons people work with this. And it has some properties. So the divergence is like, it can never be negative. So the divergence between distributions is 0 only if the distributions are exactly the same, and otherwise it's greater than 0. And then greater it is, then the larger the divergence. Okay, so and this is actually really used all over modern machine learning. So if you go on and take more advanced topics, things like variational inference, maybe some of you have heard of, and there's a really sort of hot model right now, if you will, called the variational autoencoder. It's a kind of autoencoder that uses variational inference, and anytime you hear the word variational in machine learning, basically this quantity is going to end up in there, and you're going to be trying to minimize it because you want some data distribution to look like a predictive distribution generally. And in a few classes, we're going to see something called the expectation maximization algorithm. It's going to come in there. But right now, as I said, we're going to use this to show the connection between maximum likelihood estimation, which uses the likelihood as a loss, and something called the cross-entropy loss, and the KL divergence itself. So let's go back to what we had, which was the binary logistic, just the regular logistic regression for 2 classes. So we had this idea that there were 2 labels, right? Class 0 and 1, for example. And let's just say that these true labels can be viewed as realizations of a random variable pi, which is Bernoulli, and has parameter theta. There's a lot of notation, but these are just the true labels, right? They're 0, 1, and they were generated from distribution, which tells you how to flip a coin, basically, and theta is like the bias on the coin. And then we had logistic regression, which we motivated sort of very slowly, going through the step function and then to the sigmoid and softmax and so forth. But at the end of the day, we said, okay, when we write the likelihood for this is a binomial likelihood. And so here we can think of some sort of potential realizations associated with a random variable Q that's given by Bernoulli. But now the parameter, the Bernoulli, is actually that sigmoid, right? I'm just kind of rewriting what we did last time, which was the binomial likelihood in a slightly different way. But it's the same thing. So, but the key thing is to just remember here that pi is essentially the true distribution, and we have these realizations of it that are yi, the observations. And then we have these qi, which are predicted from the predictive model, from logistic regression, and we're going to sort of think of some, of realizations of that as pi. And of course, the data, the labels are in 0, 1, and we're going to say that we have n training data points. So if we didn't start with the maximum likelihood, or the likelihood as a loss, and we started with this loss, then we would say that, so right again, pi is just the true distribution, so it doesn't have any of the parameters we care about, but it models the true distribution, and it will have, therefore, the true labels in it. And qi is the thing that is going to be predicted, if you will, by the parameters of the sigmoid. And so the idea is to adjust the parameters of the sigmoid until it looks like the training data. And so, okay. I think intuitively that makes sense, right? We're trying to basically make the distribution of the predictive model match the distribution of the labels. That's all this is saying, with this particular way to measure differences in distributions. And so now what I'm going to show you is actually generally true, but I'm going to instantiate it for logistic regression because it's kind of easier to see. So I can break this out. I'm summing over n data points, and now what I've done is I need to, according to the definition of sometimes we just say DKL for short, for the KL divergence. So the DKL, I have to marginalize over x, right? I have to sum over all values of x. But in the case of logistic regression, this is just a template x, right? But up here, it's actually kind of over y, and so all values of y, but y only has 2 values, and so when I apply this sum here, I just get these 2 values here. So one is for when y is equal to 1, and one is for when y is equal to 0. So I'm just basically plugging in the definition of the DKL using logistic regression. And then I can play around with the math and just push it around in a few ways. And just remember always that yi here is kind of the true data labels, doesn't contain our parameters, w. Pi is what's sort of hiding the sigmoid inside of it, and the parameter w. So right, I keep pushing stuff around, and what you'll see now is this has been arranged in a particular way where pi does not appear anywhere in here, right? This is only constants and yi's, which means that W does not appear in here because W is only sort of hidden inside of PI, which means I can basically get rid of that because I'm doing an argmin over the parameters. And actually now what we're left with is that this maximization problem is actually the negative log likelihood for the binomial likelihood that we had last class for logistic regression. So now you can see that there's an equivalence. If I minimize the KL divergence between my true distribution and the parameterized distribution, then I get the same result as if I were to do just maximum likelihood, right? Here it's negative, minimization of the negative likelihood, which is of course the same as maximum likelihood. And then I can go one step further, and this one's kind of obvious. This is just the definition of what we call the cross entropy, which is this right here. Just the expectation over the predicted, the true distribution of the predicted one. And so this is just kind of a lot of math and definitions, but these are all three kind of important concepts that come up in different places, especially in information theory, which sneaks its way into machine learning now and then. And so just the point here is that you can, I guess you could start in each, you could go from any one of these to the other. I think the easiest way to see it is to start with this KL divergence and say, imagine that was my goal. Well, that goal would yield the same parameter estimate as maximum likelihood, which would yield the same thing as if I used the cross entropy loss. So they're basically all the same thing. And you can, if you want to go through the details quickly, or not quickly, but on your own, step by step, you can, although I think it's relatively straightforward. Maybe you can just follow it here. Any questions on that? I think I was playing around with the product. Oh yeah, that just says the same thing. Okay, so that was just to finish off last class, where basically the introduction of logistic regression, and this was just to tie the last bit together of the different losses. So now we're going to move into thinking about classification in a different way, and the way we're going to think about it is with two kinds of classification models, which we've seen one so far. So logistic regression, it turns out, is a discriminative model, and today we're going to try to understand the difference between discriminative and generative classifiers, and then we're going to go through in detail a class of generative classifiers called, very confusingly, they're called Gaussian discriminant analysis, even though they're not discriminative models. I didn't make up these names, these are just the facts. But so don't get confused. So Gaussian discriminant analysis, and you'll see instantiations of this are linear discriminant analysis and quadratic discriminant analysis, and we'll see exactly what those are, but these are all generative models, not discriminative models. So, so fundamentally, there are two types of classifiers. There are discriminative and generative, and hopefully by the end of this class, you understand what that is. I'm gonna kind of slowly try to give it to you in different ways. Right, and sometimes you'll just hear discriminative model or generative model. Usually people, when they say these terms, they mean it about classifiers, but sometimes they peek in somewhere else. In this lecture, I mean it specifically for classifiers. And as I just said, there are many models that have the name discriminant in them that are actually generative models, and so it's very easy to get a bit confused. Okay, so what is the difference between these? There's a sort of a picture here. So I have a hint here, okay, but in any case, the way I think about it is that the discriminative model is just kind of computing a score that tells you how different the two classes are. So in some sense, it's really almost directly modeling the decision boundary. I mean, not quite, right? Because we saw we had to fiddle with the math to see that it was a linear decision boundary, but in some sense, you're just saying, what's the score? You tell me some features, and now you tell me which class I belong to. And so you're modeling the probability of y given x, and you're never modeling the probability distribution of x, right? That never appears. It's always a conditional probability estimation of y conditioned on x. So what's a generative model? Generative model, sorry, I jumped around a bit. The generative model is distinctly different in that it is always modeling the density of x and y. And that's like a really fundamental difference. It might be confusing, but as we work our way through the lecture, you'll see what I mean and why you might want to do that and what some of the pros and cons are. And typically the way so even though the way you use it looks like a discriminative model. So at the end, you're still going to make a call to probably y given x, But the way you train the model is by training essentially the joint distribution, which typically is factored like as follows. It's the probability of some set of features for each class times the probability of that class. And altogether, that's the joint. And then you can use Bayes, or well, yeah, essentially you can end up thinking of it different ways, but Bayes rule or just various forms of conditioning to back out of this to get the discriminator that you want. But you're not directly modeling this, you're only getting it by virtue of modeling a probability density over X and Y. So an example of that here, and we're gonna see a lot of that this class, is that these are like the class conditionals in a way. So this would be the probability, might say that they're Gaussian, so we're gonna see a bunch of models where probability of X given Y is Gaussian. So probability of some real valued features given that I have class 1 is a particular Gaussian, and that for each class you have its own mean and its own covariance matrix indicated here, and then you're gonna multiply it by the probability that it was in that class. So for example, maybe class 1 is 22% and the other class is 0.78%. But can you see the difference here that I'm modeling a probability distribution over X and Y, and then I'm gonna use that in order to make a prediction of Y conditioned on X, but I'm actually training, I'm actually estimating this probability distribution. Whereas in the discriminative model, I'm never, ever estimating a probability over X. This is the key difference, and we'll see why that might make a difference. Any questions just with that starting concept, yeah? But so there's two things, right? One is I have data, and two is I have a way to model those data, and three is I have a way to use the model. So in both cases, I have the exact same data set, and in this case, I'm going to choose to build a model over X and Y, and in this case, I'm simply going to choose not to. So in this case, if I were to choose to model a density over X, then I am by definition doing something that's a generative model. No, completely not, actually. So, and we're going to get to a specific example of that. Yep. Oh, we're also going to get to that. The question is, why is it called generative? So, yeah, we'll get to, what's that? Yeah. So, yeah, I think it might be the next slide. I'll just wait, because then otherwise I'll end up repeating myself. But these are all very good questions. So before we do that, I actually just found this today. I've never heard this, but I thought it was actually a really nice pedagogical story. So this is someone describing the difference between a discriminative and generative model by instantiating them as children who are learning to recognize animals at a zoo. So there's two kids, Kid A and Kid B, and they have different learning styles. So Kid A has a special ability where she can learn things, let's say, in depth. And we'll see what this means as we go on with the story. And Kid B has a special character where he can only learn the differences between what he saw. So the parent takes these kids to the zoo, and it's a very small zoo. It has only lions and elephants. And so the kids are watching a bunch of elephants, they're watching a bunch of lions, and then the parent shows them, they leave the zoo, and the parent shows them an animal and says, now, is this a lion or is this an elephant? And then the way that they make a decision is sort of indicative of whether they are behaving as a generative or as a discriminative classifier. So the first kid, who so apparently learns things in depth, starts drawing the image of a lion that she remembers, draws the image of an elephant that she remembers, and then she looks at the animal in front of her and says, like, okay, well, this looks like a lot, maybe it looks a lot like this, maybe it looks a lot like this, and sort of comparing the full image of each animal to what's standing in front of her, and then says, okay, this animal is a lion. So she, in her head, she has like a full kind of picture of a holistic lion, right, and a holistic elephant. And so this is going to be the generative model. And Kid B doesn't actually remember what each animal looked like. And you can imagine you could still answer this question very well, even if you had no idea what a lion looked like in general, right? Maybe you just remember that an elephant has a trunk and the lion didn't, and you don't remember anything else. So now you're just remembering some specific features, and you could never create an entire picture of it. So this is the sort of discriminative view of things. Right, so here, Kid A is generative and Kid B is discriminative. Maybe as we go on through the lecture and then you come revisit this when you're reviewing the slides, you'll think about more how this makes sense. Is this just confusing or is this helpful? I thought it was cute, but I already know the material, so I don't know if it's confusing. Who thinks this is confusing? Who thinks it's helpful? Okay, awesome. Okay, so let's start thinking about these things a little bit more from the little we know right now. And the little we know right now is that the generative model is going to somehow model the density of X and the discriminative is not. So that means somehow for a given number of parameters, it's going to spend a lot of its parameters modeling the distribution of X. But a discriminative model is just never going to bother to do that. So you can already imagine that this plays differently, like maybe this affects the number of parameters or other things. Right. And in particular, if you had a particular number of parameters, then the discriminative model would have the discriminative model might have a more complex decision boundary because it's not having to model all of the x's. So somehow by forcing the generative model to model the density of the x's, you're kind of constraining it in some ways and spending your parameter budget there. And again, like I'm just trying to lead you through some of the intuition here, and as we go through, hopefully this makes more and more sense.
Yeah.
So, right, and just to reiterate, the discriminative model kind of directly models a discriminative function. So for example, you know, in the logistic regression, you compute W times X, and that's like kind of a score of how much you believe the first class is likely to be true, and then when you normalize it, you get the sigmoid out of it. So, and the thing is, so in this class, I think we only present probabilistic models. No, that's not true. So there's something called SVM, which we will get to a little bit, possibly not in as much depth as in other versions of the class. And SVMs are not probabilistic models, but they are discriminative models. And so what that means is that you also build a score telling you how much you believe each class, but that score doesn't have any interpretation as a probability. It doesn't sum to 1, and so you can't think of it as like a confidence or anything. It's just sort of some arbitrary scale that matches that particular classifier. And the generative model, right, is defined by the joint probability, which we've already said we usually factor in this way. And then we can use Bayes' rule to get, after we've modeled it this way, right? So again, just to separate, we have some data. We could build either kind of, either discriminative or generative, but we decide to build a generative, then we're gonna model these probabilities. And then after we've done that, we've learned the appropriate setting of these distributions with our parameters. Then after that, we're gonna use Bayes' rule to just compute this quantity, which is the same quantity you get out of logistic regression, but you're getting there in a different way. So, and a generative model is always probabilistic. So, and the discriminative model might not be. It might just produce a score. The score is higher the more it believes in the class, but the generative model is always probabilistic. And actually, one way you can think of a generative model, because you can always generate the training pairs of data from it. It actually literally has a distribution over both X and Y. So from some model, let's say you train, if you wanted to generate pairs of data that look like what were in the training data, you can actually just draw them from that data set. Whereas for, right, and then of course, as I've also said many times, but they have discriminative properties if we apply Bayes' rule, right? So we can always get a discriminative, we can get a discriminative model out of any generative model. Is that what someone asked earlier? I thought you said it the other way around. So, it was in one way, but not the other. This is the correct way. So the discriminative models, let's think of a probabilistic discriminative model like logistic regression. So can we generate data from that? Who thinks we can generate some kind of data from it? We can't generate X, Y. Can we generate anything? Yeah. Let's really speak up a little bit. So it's hard for me to hear you. If you could just speak slightly louder. To know where to. So depending what you mean by that, I will say yes. So if what you mean by that is that if you tell it where to generate, in the sense that you specify an X, then you can generate Y's, right? Because the discriminative model is directly modeling, if it's probabilistic, it's modeling the probability of Y given X. So if you give it an x in logistic regression, you multiply x times w, you pump it through the sigmoid, and then you get a probability of the first class, and then you can sample according to that probability. So you can generate the y from the x, but you cannot generate the x. Does that make sense? Okay, and sometimes this also gets confusing. So partly, as the years go by, the lingo shifts a little bit, and right now it's very common to call unsupervised models for which you're modeling the density over, say, a bunch of images, and you're ignoring the label, so it's completely unsupervised. People often call these generative models as well, and that's a little confusing. So in this lecture, when I say generative model, again, I mean for a supervised problem where we're doing classification. But just so that you know, in case you're very interested and you're reading on the side or you go take other courses, you'll also hear this word for just P of X, where there's no notion of a Y. So one thing to think about is that the generative models, because they're modeling a distribution over X, they have very strong and explicit assumptions on the properties of X, right? Like I'm actually defining the distribution of X, whereas the discriminative model is I don't care, whatever X you give me, I don't care what distribution it is, I'll just pipe it through something and get a score. But in the generative model, I will say, for example, these x's from this class, they are specifically Gaussian with this mean and this covariance, right? So this is a very strong assumption. So I wrote here, the discriminative models may only implicitly capture things like correlations between x. So you can imagine that when you train logistic regression, that it might downweight two features that are correlated because they're correlated. So it somehow can tease these things apart, but it's very indirectly because it doesn't model the distribution over x. And so because of this very strong explicit assumption, the generative models are not as robust to model assumptions as the discriminative ones. So discriminative ones are making fewer assumptions, and so they're generally more robust unless you know that all those assumptions are correct. But if you actually know that your data adhere to those assumptions, then generally it's always better to use a model where you have the assumptions are in there, because it's sort of pinning down the space a little bit. If you know they're true and you pin it down, then you're almost certainly always going to do better unless you have infinite data. Okay, so that's the sort of general idea of discriminative versus generative classifier models. And the key idea, I'm just going to say it over and over, is that you're now modeling also the distribution of x. And so now we're going to go through and look at some examples of these, but I'll take some questions. When you say prior, what? So actually, I just was looking through some of the notes today. Periodically, I actually don't like some of the terminology. So if you read ahead, I actually went through, and I think it's my fault because in my slides last year I had the word prior, which I have now systematically removed, except on one slide. So if you're, so there's, let's go. So if you go to to here, and sometimes you'll see this called the prior, and I guess I had that in my head. And now repeat is this what you meant by the prior when you said prior, or you meant something else?
I was thinking about it in the context of Professor Yi's lectures, but the prior distribution and what if that's
I see. Yeah, that's a little different. So earlier in the course, when you were looking at like Bayesian models like MAP, or being sort of fully, MAP is where you take the likelihood, you multiply it by a prior. The prior is your prior belief on the parameters, like a distribution over them, right? And then if you do MAP, what you get is you maximize that, and you still get a point estimate. You get one estimate of the parameters. If you're like fully Bayesian, then you integrate it out and use the full distribution. So this is different because we're not putting a prior on the parameters here. This is somehow quite different. We're just saying I'm going to choose to model a density over X. So that you could do similar things to what we did earlier in the course here. Is you could start putting priors on the parameters of logistic regression or of other things, but that would be sort of an orthogonal point to what's in this lecture. Any other questions? Okay, so we're going to talk now about a class that I've already shown you, even though you didn't know. It's Gaussian discriminant analysis. Basically, that's going to be when this term we model with Gaussians. And we're going to have one slide at some point talking about this term, but this is a much easier term. Like I don't have to think of anything fancy because this is just probably the y equals like a or b. Like it's just a number, so it's not anything complex. And here I have to decide though, like, is this a Gaussian? If it is, what kind of Gaussian? Maybe it's not a Gaussian. So this is sort of the more complicated beast and the thing that affects the model in the end somehow more. And right, and just, I'm gonna repeat a couple of points this lecture just to really drive it home. It's called Gaussian discriminant analysis. Officially, if you Google this, it's not gonna have quotes there. I'm putting the quotes there to make sure you know this is actually a generative model because it's modeling the joint probability of X and Y. So just try not to get confused by that. And right, so an example would be for two classes, which sort of the idea is here is I model each of these as a Gaussian. And if you have maybe seen somewhere else clustering or something, this is nothing like that. This looks like two clusters, but and we'll get to clustering in another, I think maybe in the next lecture. In clustering, you don't know the class labels. Here, we always know the class labels because it's a supervised problem. And so I have basically a Gaussian density for the first class with its own mean and covariance, and I have a Gaussian density for the second class. And that's basically Gaussian discriminant analysis, except that we're going to talk about it for another hour or something like that. Right. And then, as I said, the P of Y term is pretty simple, right? It's just like a Bernoulli, like, so it might have a parameter just on like probability that it's each one. Okay, so assuming we're going to have this Gaussian discriminant analysis, what are some of the choices we could make? If you go think about the parameters, basically it's a matter of saying like, how much do I constrain those parameters, right? So I can do different things. I could make the means be the same. I could let them be different. I could let the covariances be the same. I could let them be different. I could make the covariances maybe be spherical. I could make them be diagonal. I could make them be low rank. All kinds of things. And so these are, so there's sort of an infinite possibility almost of Gaussian discriminant analysis. And we're going to go through two of the most common flavors and the implications of those choice on the decision boundary. So first of all, we're right now in this lecture and in the class, we're always going to assume that the two means are allowed to be different. And that's because we kind of expect the classes generally to be sitting in different parts of the space with respective features. Although you could, in principle, have them be the same. It would probably be a pretty weird way to do it. I didn't look. I assume someone has actually done this somewhere, but I don't know for sure. But let's just assume always that the means are allowed to vary because like we want separation between the classes to get a decision boundary. So given that, maybe we have two identical spherical Gaussians, and I'm just introducing some terms here just so you learn them. So spherical means that it looks like this, right? The variance is only on the diagonal, and it's always the same. Sometimes we call that an isotropic Gaussian. I think you saw this in the first half of the class. So something else we could do is, again, right, we could say, and so just to repeat, like that means that these things look like circles. Those Gaussians, these are the level sets. And so if it's spherical or isotropic, they look like these round things. If I loosen that constraint a bit and I let them be arbitrary covariance matrices, then as you've again seen earlier in the class, then these level sets can start look like ellipsoids that are drawn out in particular directions depending on the eigenvalues of that matrix. So, and in the most general case, the means are allowed to be different, the covariances are different, and they're just totally arbitrary. And so in such a case, then you have 4 parameters. If you start tying things together, if I make the covariances be the same, then I would only have 3 parameters, right? And we're going to sort of walk through now the implications of some of these things on the decision boundary. Remember, the decision boundary, like it was a line for logistic regression, and it's again analogous to like a regression curve. And as it gets curvier, you kind of have a more richer, higher capacity predictive model that can separate things better in that space. And everything I'm going to go through, I'm just going to do the math for 2 classes and like 2 things we're classifying, like class A, class B, lion, elephant, dog, cat. But everything I'm going to tell you applies more generally as well. And there's some pictures just to give you a visual of that toward the end of the lecture. Okay, so how are we going to do parameter estimation? We're going to do maximum likelihood. It's a probabilistic model. So let's do maximum likelihood as we do. And we have data from k different classes. I said we were going to do 2 classes. I guess some of the slides are k classes. I guess the pictures will always be 2 classes. And the x, so this is again, the x that you see from regression, and the y similar, except that it's discrete labels. You can label them arbitrarily, they're not ordered. So conditioned on the class, so for a particular point, it only comes from one class, right? We know it's either an elephant or it's a long and because of that, the likelihood decouples according to each class. So I'm gonna sum over each class, and for each class, I'll look at only the data points that belong to that class. And that just makes things look a lot cleaner and actually quite simple. But again, you can see here, this is literally modeling the joint, and it has a set of parameters, the mean and the covariance for each class, and the likelihood it decouples by class. And again, that's how you know it's a generative model. All right. So what emerges if you do maximum likelihood here, and you can do this in closed form, and we'll go through it in just a second, is that you get updates that are super intuitive. So because the likelihood decouples by class, it basically is saying for class K, imagine that's this class here, these blue points, you know which points belong to that class. For just those points, you're doing maximum likelihood over this, right? And so if you want to learn the mean and the covariance, they don't appear in here. So this term is going to go away. So you're basically just doing maximum likelihood of a Gaussian. And we all know, you've seen this, right? It's just a mean and empirical covariance, basically. So, but we'll just kind of quickly go through that.
What if you have no idea what your distribution of data has?
If you have no idea what distribution they have, then you probably should use a discriminative model, where you're not modeling the density of x. Yeah. I mean, it's conceivable you could just use something very flexible. So I guess in a couple of classes, I can't remember exactly how it unfolds, but you could do something more. Well, who has an idea? Imagine that one class right now is represented by a Gaussian. How could I get a richer representation for that one class just using Gaussian? Anyone have an idea? But that's not going to make it a richer class of models, right? It's just so when I say how can I change the class of models, that means that I'm not changing the parameters. So you can add Gaussians together, something called a mixture of Gaussians. So right now, I think that one class looks like essentially one Gaussian blob. What if I said I think one class looks like many Gaussian blobs? Now I can capture something much more complicated, right? And we're going to learn that model later on, not now. So that would be one thing, but in general, if you want to build a classifier and you don't have you don't have a good sense of this, you should probably just use a discriminative model. Right, and so again, like you've seen this a million times, which is kind of drive it home that we use this all over. We can justify these updates here, like we can actually go through the derivation by setting the derivative to 0 and then getting it. So, right, what we want is, so P of y has been obliterated from here because these parameters don't appear in P of y. It should I guess, be on the slide before I obliterate it, but we're trying to find the mu and the sigmas. Here it's not a full covariance matrix, just diagonal, that maximize this, right? So and we're gonna just take the log of it, which we always do, and then we're gonna say that it factors by data point, so now we're summing over them. Then all I'm doing here is pushing in, replacing that it's a Gaussian. So now this is just a Gaussian density that I've put it in with, plugged in. And then here, of course, 2 pi is not relevant, so that drops out. And so we need to minimize with respect to both sigma and mu. And so the question is, can you do them independently? Are they tied together? So maybe you've seen this in another class, but I think we all know the answer probably. But so let's try and solve for the mean first. I take the derivative of that thing that is my new loss after pushing it through to the end, and then I basically set it to 0, and then I get what we've all seen 100 times, which is this is the estimate of a mean. So that's how I'm going to set the means for each Gaussian in my Gaussian discriminant analysis, which is a generative model. And this is really the way, this is the mean of a Gaussian for one class, right? And it doesn't depend on sigma. But as we're going to see, if we try to solve sigma, it does depend on mu, so you kind of have to do it in that order. And if, again, like you just get the empirical variance, so nothing fancy there. So right, and what about setting? So again, I've just been looking at this. said that we can just use the usual thing, compute the derivative, set it to 0, and then in this case, we can solve analytically, get the updates for every mean, every covariance. But how are we going to set this y here? Because we need y, and what I've just showed you here are the means and the covariances only for this first term here, the probability of x given y. So you can think of this in two ways. This p of y term from here. We can think that we're just going to compute it empirically from the data. So someone gives us a data set, has a bunch of cats, a bunch of dogs, and if half the data set is dogs and half is cats, then if we were to empirically estimate it, then this will be 0.5 for one class, 0.5 for the other. If there was a third dogs and 2/3 cats, then set it accordingly. So just some empirical estimate from the data. The other thing you might do is you might actually specify it with prior knowledge. So maybe you have some, like maybe you're like working with a physician, and the physician knows the prevalence of some disease versus another disease. And so you actually just say, hey, like out in the big population, what is the prevalence of this thing? And you set it that way. So can anyone tell me why you imagine you had, like you have the data because you're training the model, right? So why would you ever do B instead of A? Not quite. Not quite. Any other ideas? Bingo. Yeah, so to rephrase what was just said in case you couldn't hear it in the back, sometimes you have data sets where you have sort of really enriched for one class because it's very rare. So this happens a lot in disease modeling, is you have some super rare disease and you want to build a predictive model, but it happens like 1 in a million. And so like you don't want to use that ratio because it's sort of cumbersome and you have this crazy amount of data that you don't really need. So and also you're collecting things in the clinic and you're trying to get lots of people with the disease to build this model. So in the data set you have that you're trying to build, maybe you have totally enriched this 1 in a million disease and it's actually 50-50 in the data. So if you just use the empirical distribution, you're actually not going to make predictions that are relevant to the true population, maybe relevant to a population where it is 50-50. And so that's why you might want to do it. But generally in this class, I think, well, actually, I won't say that. We may do both of these in different places. So, okay, so now we know how to set all three of these parameters, right? So these first two parameters, again, they come from the Gaussians, which are from the first part of this. And then this third one we just described, we either set it empirically from the data as a very, very simple statistical estimate, or we define it a priori with auxiliary knowledge. Okay, so let's take a look at the decision boundaries that are implied by these models. We, again, in the last class, we saw the decision boundary was linear, so what do they look like here? So remember also that the decision boundary, we get it by taking a model, and in this case, even though we have a generative model, we can use Bayes' rule to compute these things, which are probably y given x, just as we got from logistic regression. We set them to be equal, and then we see what kind of a function of x is it. If it's a linear function of x, then we have a linear decision boundary. So right, so let's do that for Gaussian discriminant analysis, and we're going to do it in a few different ways. So first, let's assume that we have identical isotropic Gaussian covariances, something I mentioned before, right? That's when they look like two spheres like this. So given that assumption, then we can work through. And we're also, right now, we're going to assume that the probability of each class is the same. So, right. Given that assumption, now I'm just taking the joint for class A and for class B, and I'm saying that they're going to be equal in order to find the decision boundary. And of course, because I set these to be equal, these two things are going to drop out, and I just get left with the two Gaussians here. So this says the Gaussian that belongs to A has to look like the Gaussian that belongs to B. And I make it look like this. Going through, it is a Gaussian, and then I can take the log because it doesn't violate the equality, and then I can actually now again just instantiate fully the densities there, so I get this whole sort of long drawn out thing. I know I went a little fast here. I'm just trying to. I mean, you can easily just follow this at home. There's nothing fancy going on here. It's just some manipulation. But I'm going to carry this last thing over to the next slide, so that's just rewritten here. And now if you work through all of this, what you find out is the function of x you get is this. You have a quadratic within the mean of A, and not a quadratic. You have what looks like basically a decision boundary where the points, I can rewrite this as like a norm, and it basically is saying that the decision boundary is anywhere where x is equally far from each of the two centers. So if these are the two centers, and that's only true when I have a diagonal covariance, because that was an assumption that I made when going through this map. And so the result of that, if you think it through, is that this entire line here is the decision boundary. All x's here satisfy the property that they're equidistant from the two means, right? Like this one is further away from, it's the same distance from these two means, but it's further away from the means than here, but these are all equidistant. And so this actually has the same kind of decision boundary as you get with logistic regression. Does that make sense? Any questions? Yeah?
Why is this very not variance?
Because it's just a matter of being equidistant, and here the variances would just make those level sets kind of like have different values, right? Like all that would happen if I changed the variance is that the value associated with each level set would be different, but the sort of geometry here would remain the same.
They're not isotropic.
We're getting there. That's next. We're next. Hang on. Okay, so right, we didn't do the general case. We assumed one equal class prevalences and equal spherical covariances. So we're going to do a few variations and see what happens. So what happens if we let the covariances be equal, but of arbitrary shape? Who thinks this will yield a linear decision boundary? Who thinks it will yield something more complicated? Not very many brave people, but okay, the second one is winning in the vote. Let's see if it wins in the slides. So in the isotropic case, the boundary was dictated like this, and that led to a line. And I'm not going to go through it, but it's almost the same. Like you can just go back to that derivation, and where previously things kind of canceled out nicely because of the diagonal elements, now they won't cancel out nicely. And what you're going to get out is something that looks like this, where this term wasn't there before. Because it wasn't there, this was just like a norm, right? And I had the norm with respect to the one mean and the other. But now I can't, because this covariance matrix, I haven't let it be simple, I've let it be arbitrary, but the same. So each of these are now ellipsoids, and they're the same kind of ellipsoid for both classes, right? Because they have the same covariance. So I can actually pull out some of our tricks from the first half of this class. I can do an SVD of the covariance matrix, and I can basically use it to kind of whiten or diagonalize X. And so once I do that, I actually end up with the same kind of geometry I had before. I now am just kind of in a different space, and it still is a linear decision boundary. So actually, that actually doesn't help us terribly if we allow the covariance matrix to be arbitrary. What's going to actually help us to get something richer is if we decouple the covariance matrices. So we're going to do that in a second, but apparently not just yet. So first you can say, what happens if the class priors are not equal? Before these two things were canceling out, but if I leave them in, then I have to leave them in the equality. But we're really just kind of adding a constant to the system. And so I won't go through the details, but it actually leaves the decision boundary just the same in terms of the fact that it's a line. It's not the same line, but it is still a line. Okay, now finally, what happens if we also allow the covariances for each class to be different? Right, so now we get the full generality, where here these were tied together before. Now they're just completely different. And when I do that, I guess in this case, oh yeah, right, and now this is fully general. So these are these sort of constant terms you're going to get from allowing the class prevalences to be different. And now you're getting this very, very general thing here with its own covariance matrix separate from this. And can anyone see, you can see that I can't use that SVD trick, right? Because if I use that SVD trick here, that same SVD is not going to be applicable to a different covariance matrix. So I can only whiten one of these or diagonalize one of these, but I can't do it and maintain the equality. Because if I do an SVD that diagonalizes this and I apply it to this side, it's not going to be diagonal because it's not the same covariance matrix. Does that make sense? So I'm really stuck with these. Like I can't get this to look like the first case where they're tied together. And so, in fact, we now have a thing that's quadratic in X, and the decision boundary now looks quadratic and not linear anymore. So just, I haven't given these things names, but these things have names. And so when the class covariances have any shape at all, but as long as they're equal, then the decision boundary is linear, which we just saw, and we call this linear discriminant analysis, which is a generative model. When the class covariances are unequal, then the decision boundary is quadratic, and we call it quadratic discriminant analysis. And as I said, all these results also hold for the multi-class case. And so just to show you a picture of what that might look like, so this is the linear case, and you see these are straight lines, and these are sort of like Voronoi tessellations. Every line here is straight because everything is a linear decision boundary. Just in the multi-class case, instead of dividing the plane or in higher dimensions, you partition the space with lines. In contrast with QDA, these are all quadratic curves. And so you can see that you can get a more complex way to divide up the space like this. And because you're allowing for more covariance matrices, if there are sort of arbitrary full rank covariances, then you're also incurring sort of a penalty for those. You have to estimate way more parameters. So each covariance matrix has d squared divided by 2, roughly, right? Because it's a symmetric covariance matrix. And then you define only one for k classes. And so you get all these extra parameters. And that could hurt you. As always, you have to decide, like, is it worth it to use more parameters or not? And that's going to depend on how much data you have and how the bias variance trade-off plays out. And although we saw a very technical, precise bias variance trade-off, generally you would assess this by using model cross-validation. You'd say, oh, let me try it this way, let me try it this way, and see which one works better. Any questions? Okay. I tried to remove this term posterior from everywhere, but I didn't. I would like to now call this the predictive conditional. So don't just ignore this. It's not. We're not being Bayesian here. I just edit it now. I'm scared to do anything after last time. Okay, so this should say, and it'll say on the next slide there, predictive. What does the predictive distribution for linear discriminant analysis look like? So far I've talked about what do the Gaussians look like, how do we estimate them, how do we get this parameter, and then depending on how I make choices for the covariance, what does the decision boundary look like? But I haven't actually gone through and said, what does the model look like when I use it as a discriminative model, even though it's a generative model? That is, I use Bayes' rule to compute this after having estimated these quantities. Sorry, it's jumping around a bit. This is the same line. And so what that looks like is this, which is proportional to the right. These are the Gaussians. And I'm just doing one class here. What is the probability of y equals a? There's only one Gaussian here. It's the Gaussian with a mean and covariance for a. And actually, the covariance is for all classes, so it has no letter associated with it, times that probability. And then I'm just going to say that's proportional. Like, I'm proportional because I don't care about x. To the part of the Gaussian density that looks like this. And similarly, for I can do the same kind of thing for that probability y equals b. And now if I normalize these and I crank through the math, then it's possible to show that actually it takes this form. Does that look familiar?
Interesting.
Just shout out. What is this model? This is logistic regression, right? This is the parameter from logistic regression. What I haven't told you on the slide, I said I can make it look like this, and I would have to set W to be a very specific value, right? So all I'm saying is that if I start with linear discriminant analysis, I use Bayes' rule to compute the predictive distribution, and then I'm manipulating things. It actually looks like logistic regression. What's going on? We just done like a big circle, and this was just all a waste of a class to see if you would get the trick. No, it's not. Right. This is logistic regression. And also you could extend this to multi-class softmax. So if you had multiple classes here, then you would also get a softmax out of this. Okay, so what I just showed you is that the linear discriminant model can always be written as a logistic regression model, right? I didn't show you exactly how, but I said it can be shown that it takes this form. That form is logistic regression. But the converse is not true, and that's why there is a difference between these things. So not every logistic regression model can be written as LDA, and that's why these things are different. And so the conclusion from that is that LDA makes strictly stronger modeling assumptions than logistic regression, and logistic regression is therefore in some sense a more general model. Does that make sense? Okay, so when the LDA assumptions are correct, so in particular the data is related to the question from before, if you know that they take these Gaussian shapes, then you may as well use that information. Generally, if you have any information like that you know to be correct, then you should include these things in a model because it's almost always going to help you, and that's true in this case. But as you get more and more data, then it matters less and less, because the idea is that you're telling it something about the data in the presence of limited data, and that's what's going to help you. But if you have sort of infinite data, then you don't need to tell it anything. It can kind of figure these things out. And this sort of trend is generally true for generative versus discriminative. And so the trade-off is that if you don't have a lot of data, then if you can impose some structure via a generative model, then you may want to do so. But if you don't know how to impose that structure, then you should probably just directly model a discriminative model. Okay, so everything I talked about so far for these generative models was for Gaussian discriminant analysis, where they were real valued features, right? Because the x's were modeled by Gaussian densities. And so what happens if the x's are discrete? So who can think of an example where the x's are discrete? It appears all over my research. If you know at all what I do, maybe that's a thing. But maybe you don't. Yeah, so that's what I mean by discrete here. Yeah, so what can you think of just a real world example where that, I mean, there's lots and lots of them where that happens. So there's a city, yeah, right. So, and some particular fields, this arises a lot. So I do a lot of computational biology. So if you have sequences of data, so imagine you're trying to predict a disease from like your nucleotides, your genetics. Like who's done 23andMe here? Anyone? Very few people. Okay, so in any case, one day, I'm sure we'll all have our genetics read, but if you have your DNA sequence and you want to, you could imagine, I mean, people do these things, you build predictive models for it. Or you're doing, like I build models for gene editing, and you're trying to decide from a particular sequence, like whether I should deploy my CRISPR gene editing here or not. So you have nucleotides or amino acids there. These are discrete. Another place where this commonly comes up is in natural language processing. So if you want to predict whether a certain phrase has a sentiment that's like positive, maybe you're doing a political analysis of the news and you're scraping some blogs or something, and you're building a predictive model that says, is this like, I don't know, pro-Trump or anti-Trump, then you're going to have discrete symbols, which are the text on the page, right? So these are two fields where these things are very, very common. So if you want to build a generative model for these, now I can't use Gaussians because it's not a distribution for discrete things. And so a very common model assumption and by consequence common model that gets used is you just assume that each feature is independent of the other. So if you have d discrete features, so maybe like if you had a nucleotide sequence, it's like, is there a letter A in position 1? Is there a letter T in position 2? Things like this. Then you just assume each of these are independent, and so they just factor by multiplying together. And then it means it has very few parameters, because as soon as you allow these things to not be independent, you basically need parameters for their pairs and for all of their kind of couplings. But if you assume they're independent, you only really get kind of one parameter per feature. And if you do this, there's a very, very famous model called naive Bayes. And it's naive because of this assumption of the independence of the features. And in fact, I don't actually know why it's so famous, because I think it doesn't work very well for this reason. And you can also augment these in various ways to mitigate this assumption of independence. And so I'm not going to go into the details of it, but you could imagine instead of that model of independence that you choose this thing called tree-augmented naive Bayes, which actually is a model that does work really, really well. So it's kind of a fairly simple fix. And you now model the dependency among the x's not as fully dependent, not as fully independent, but as some factorization that looks like a tree. And so you can approximate pretty complex distributions between the features. And then there's a particular algorithm that goes like this, but we won't go into it. And we'll be very happy to know that I have run out of slides today. So that's actually the end of the lecture. But we can. Do you want to have like some questions, like Q&A, or a sort of unofficial office hour now since we missed one? Well, you guys can go, and I'll stick around. And if there are questions, like we have to. Actually, we have 20 minutes, so I'll stay here 20 minutes, and we can have like a little office hour.
Oh, you do Uber to it?
It won't take that long.
Okay.